All right.
Yes. Let's see
Good
what
afternoon.
could be possible.
Shut up, Galen.
Today I'm going to
Get this one right. The last one right.
there are important examples showing you how to apply the failure theories on design and analysis process. And from tomorrow, we are going to start checking. Some of you may have heard this before, but many of you have experience about that. It's very important concept. This chapter, chapter 6, has many details and equations, so make sure that you are following the material. So we are gonna go over that. After that, we are gonna cover design of the shaft. So this is what we are gonna do for the next 2-3 weeks. If you have time, we cover power screws as another mechanical components. We are gonna do the design analysis for that component. All right. Let's start with the first example. So there is a small pin, 6 millimeter for diameter of this pin, is made of ASTM cast iron class 40. This mechanical component is supposed to take an axial load, axial compressive load, with the magnitude of 3.5 kilonewton combined with a torsional load of 9.8 kilonewton meter. Not kilonewton, just newton meter. So the torque, the unit is newton meter, force is 3.5 kilonewton. Find factor of safety with respect to failure according to three theory. Brittle Coulomb or BCM, modified Moore, and maximum normal stress theory. So the first two would be applicable. The last one just to compare. It's not the failure theories that we are going to use for the design or analysis. So this pin is going to look like this. Six millimeter, force of P with 3.5 kilonewton applied, as well as torque. So we are given with mechanical component. We just would like to do analysis to find the factor of safety. if the factor of safety is less than 1, the failure occurs. If it's greater than 1, it should be safe. Good? So, just one simple question. Where would be the critical section? If I ask you, because this is the critical section is the where that we are going to start doing the analysis for that. If we don't know where it's going to be there, we cannot start the class. So where should be, or where would be the critical section in this mechanical component?
The wall.
Wall here. Okay. Any other thought?
The wall itself.
The wall is correct, but if you look at this compressive load, it's gonna make the same amount of the force and the stress in any section. So if I just look at the axial load, any section can be critical section. If I look at the torque, it's gonna be the same. So any cross section is gonna be the same amount of the torque. So it means wall or any other section can be a critical section. So no matter where you could break. So if I apply a force, then, if I apply a force like this, since the wall has the largest distance from the force, we are gonna see the moment maximum at the wall. So the wall is gonna be the only critical section. But based on this type of the loading, any section can be the answer.
Because it's even along the entire thing because there's no moment.
There is no moment.
I mean, there is, but
It's gonna be the same over the P. So it's not always wall.
all in all, you just
Good. So let me start with this one. In maximum normal stress theory, if you remember, the factor of safety was the minimum value of sigma 1 over SUT and negative sigma 3 over SUC. You should find this, and pick the minimum value among these two. And that would be the factor of safety for this. So I need to find the ultimate strength for that material. ASTM 40? Yes, it's a ASTM cast iron 40. Table A24. It provides the mechanical components of cast iron. So ASTM 40 is right here. The first this column is representing tensile strength. So SUT would be 42.5 kPSI, and for compressive strength, which is the ultimate strength for compressive loading, is going to be SUC 140 kPSI. So table A24. The units that I have here would be Newton and Newton meter, and the distance or the dimension is in millimeter. So I should change the kPSI to Pascal. So unit conversion is going to be SUT. It's going to be the unit conversion factor would be 6.89 times 42.5. It's gonna give me in megapascal. So 6.89 would be the factor, the conversion factor. If you can find this factor easily by changing pound to Newton and inch to the meter. And SUC would be 6.89 times 140, which is 965 megapascal. So now if I find sigma 1 and sigma 3, I can find the factor of safety for the first theory. So I should see what would be the stresses applied to the critical section, which would be any section on this pin. So due to this torque, we are going to have shear stress. It's going to be T C divided by J. C is the half diameter. J is pi d power 4 divided by 32. 60 T pi d power 3. T is 9.8 Newton. Diameter is 6 millimeter. Change to meter power 3. It's gonna give me 231 megapascal. This is the shear stress due to the torsion. We have axial load. It's the other load. So the normal stress, this axial load can make normal stress of sigma. It's a compressive load. So negative, whatever is the force, 3.5 kilonewton divided by area, pi d power 2 divided by 4, negative 14, 10 power 3, pi 6 millimeter. We should change it to meter square. Negative 124 megapascal. So I have this as a normal stress, this as a shear stress. We don't have any other. So sigma A and B would be sigma x plus sigma y divided by 2. We don't have sigma y, so it's going to be sigma x divided by 2 plus minus sigma x minus sigma y, which is 0, divided by 2 square plus tau xy square. Negative 124 plus minus negative 124 divided by 2 square plus 231 square. I will get sigma A equals to 177 megapascal. Sigma B would be negative 301 megapascal. These are principal normal stresses, and the third one would be 0. If I rank them, sigma 1 is greatest, sigma 2 is the middle, and sigma 3 is the smallest. Sigma 1 would be 177, sigma 2 is 0, and sigma 3 is negative 301 megapascal. Any question on this? So just plug in the numbers there, and would be minimum value between sigma 1, 177 megapascal. Since both I'm going to use the megapascal, I don't need to multiplied by 10 power 6. So SUT is 293, and negative sigma 3, which is positive 301, divided by 905. Minimum value between 1.65 and 3.2, which is 1.65. 9065, yes, thank you. 965. This is for first time. So let me keep SUT is 293, 965. Be consistent. I'm using the units. So if it's a Newton and meter, we should use Pascal. If it's pound and inch, we should use PSI. Yes.
So, is that, because neither of those divisions give you a number greater than 1, is that 1 over n is equal to?
Thanks for catching that. It should be SUT
Okay.
divided by sigma 1. Just revise this. If sigma 1 is greater than this, then we are going to have failure. So I should use 965 divided by 301 and 177. Second theory is brittle flow mode. It's going to look like this. So we should see at which quadrant we are in, then we can use the proper failure criteria. So when I look at sigma A and B, sigma A is positive, sigma B is negative. So I end up to fourth quadrant. Sigma A is positive, sigma B is negative. Sigma A is positive, sigma B is negative. So I can get factor of safety by using the equation of that line. Sigma A, which is 177, divided by SUT, which is 293, minus sigma B is negative, negative 301, divided by 965. This is in megapascal, this is in megapascal, so I can use both in this ratio. Equals to 1 over n. So n would be, just flip this, 1 over 177 over 293 plus 301 divided by 965. It's going to be 1.09. This is for BCM. And the last one is the modified mode. Modified mode theory is gonna look like this. So And brittle column, we just connect SUT to negative SUC. But for this one, it's coming down up to negative SUT, and then this line is gonna start from this point. So we should see at which area we are in, then we can use the corresponding failure criteria. So we know that sigma A is greater than 0 and sigma B is negative. So it's gonna be either case 2 or 3. So we should check if the absolute value of sigma B over sigma A is less than 1 or greater than 1. So absolute value of the sigma B over sigma A sigma B is 301, negative 301 divided by positive 177 is greater than 1. So we are going to use equation 532b to find the factor of safety. Everybody can see how did I end up to this equation? So if this is the case, I can find 1 over n equals to SUC 965 megapascal minus 293 divided by 965 multiplied by 293 multiplied by sigma A, which is 177, minus sigma B, which is negative 301 divided by 965. This is how you can find n. If you do the math, you will find n equals to 1.36. Just compare these three factors of safety. The most conservative is gonna be this with the lowest factor of safety, and we expected that because the safe zone is gonna be the smallest one, and then it's gonna be modified Moore theory, which is gonna give us 1.36, and the least conservative method is going to be a maximum normal stress theory with the highest. Now, if I want to show sigma A and sigma B on graph, if this is SUT with the value of 301 megapascal, this is going to be negative SUT negative SUC with the value of negative 965. SUT was 293. Thank you. So negative SUT would be negative 293. Sigma A was 177 somewhere here. And sigma B was negative 301. It's going to be a slightly So this is the point of the load. If I connect this to this one, I'm gonna get the failure criteria for brittle column mode. If I go with this, I'm gonna get modified mode. And if I extend this, I will get maximum normal stress theory. Now, if this is point A, the load, if I connect the origin to point A and continue, it's gonna have intersection with each line at these 3 points: point B, point C, and point D. So let me start with this one. For brittle column mode, we got 1.09. Now, if I divide OB by OA, OB, it's a load line. Point B is intersection of this load line. With the failure criteria, I will get a number close to 1.09. For the second one, I got 1.36. It's going to be OC divided by OA, 1.36. And for this one, it's going to be OD divided by OA. I'll end up to 1.65. So graphically, I can show the factor of safety for this problem. Any question on this? So now let's look at a design problem. We are going to start from scratch up to the last point, which is coming with the diameter of the shaft. So there is a shaft that we would like to design its diameter. So we don't know how much it's going to be to support this loading. 2 pulleys with given dimensions have been attached to this shaft. 1 pulley has been connected to the motor. The other pulley is going to transmit the torque and the power to the other direction of the shaft. So the tension on the belts are given. So 300 over there, 550 pounds. On the other side, 360 here, 27 pounds on the other side of the pulley. So you have seen this problem before to find the critical section. Now we would like to use that knowledge to design the diameter of the shaft. So the shaft is made of ASTM cast iron grade 25. So we know the properties of the material. We would like to design so it's a typical mechanical engineering problem that you might see. And we are doing the static failure. On chapter 6, you learn how to do the fatigue analysis to complete your design. Alright. All dimensions are given. So you can check the input torque should be the output torque. 300 times the radius, which is 4 inch, minus 50 minus 4 inch should be equals to 360 times 3 inch, which is the radius, minus 27 times 3 inch. If you doubt, you can check. You will end up to 1,000 torque coming to the shaft, almost 1,000 pound-inch going out of the shaft. So torque in would be 300 times 4 inch minus 50 times 4. It's going to be 250 times 4, 1,000. Torque out is, I'm just doing double check, 360, this force times the radius is making torque in the negative of x direction. So negative 360 times 3 inch plus 27 times 3 inch. You will get negative 999 pound-inch. So it's, I can round it to say 1,000 coming, 1,000 going up. If the summation is not 0, the shaft is going to speed up. So we are going to have acceleration on the shaft. So the shaft is going to speed up over the time. First, find critical section. These loads and this load are the only loads applied to this shaft. So I have this load applying on the plane xy, and this load applying on plane xz. So I'm gonna have two shear force diagrams in two different planes. XY plane in XY plane at point B, I'm going to have the force of 350 pounds. 300 plus 50, it's going up in positive y direction. What would be the reactions at point A and D? You can find that the reaction would be on the opposite direction. It's going to be negative 222.7 and negative 127.3. It's going down, it's negative because y direction is going to be in the opposite direction. If you draw bending moment is going to be about z-axis. This is y-axis, this is x-axis, these forces making rotation about z-axis. It's going to look like this. With negative value of this distance is 8 inch. I skip the steps. I'm just drawing the bending moment diagram and shear force diagram for these two planes. So it's going to look like this, which is going to make MZ. The other plane is XZ plane. This is z-axis, positive of x-axis. This is x-axis. Positive of z-axis is going to be in this direction. The force applied here would be 387 right here. 300, 360 plus 27, 387 applied at point C. This force should be supported by these two bearings that we have at point A and at point D. So you can find the reactions in Z direction, it goes up. The positive direction is going to be this direction. So RZ would be negative 105.5 pound, and RD would be in Z direction. Negative 281.5. So bending moment diagram is gonna look like this. It's my. How do I know it's my? It's z-axis. This is x-axis. The moment is going to be about the other axis, which is y. So it's making rotation about y-axis. At point C is going to be 1688. Any questions so far? Yes.
So the forces are in foot pounds and the final answer is in inches over there. Is there any
I made a mistake before. This one?
Yeah.
It's torque. So it's a foot. I mean,
It's pound force.
Oh, force?
yes.
I thought it was okay.
Any other question on this? Now, by looking at the bending moment diagram, I should decide which section is going to be the critical section. So point B here, it's going to have the greatest MZ, but here point C is going to have the greatest MY. So I cannot decide which one is going to be the critical section. So since I have circular cross section for shaft, I can find the summation of the moment, which would be mz at point P square plus my at point P square. Same thing for point C in Z direction and Y direction. So here I have MB at Z direction. What would be the MB? This is the MZ at point P. What would be the MB at point? What would be the MY at point P? So the force times this distance. So MBY would be the force times distance, which is 8 inch. Negative 1782 pound force inch. Same thing for point C. Point C, I know what would be the MY, but what would be the MZ at point C? I can find MC in Y direction. This force times this distance. So negative. I'm looking for MZ. Okay. For point C, it's gonna be negative 281.5 times the distance, which is 6 inch. Negative MC in y direction. MC in z direction. Negative 127, not this one. I'm looking for the bending moment of point C about z-axis. And this one should be corrected. It's going to be about y-axis for point B. So negative 127.3 times the distance from this point, which is 6 inch. It's going to be negative 763. So if you plug in the numbers here, you will end up for point B, 1972 pound inch. For this is going to be 1852. Just compare point B and C. Point C is going to see the greater moment, so we are going to do the design for section C. Thank you. Point B. Point B has the greater bending moment, so section B is the critical. So I could find the bending moment distribution over the beam, and by looking at that I could figure out where should be the critical section, but also I have the torque applied to the shaft. If I draw the torque diagram, if this is the torque, which is M about axis of shaft, which is X, over x-axis, from point A to point B, we don't see any torque. 0. From here to here, you don't see any torque. At point B, I'm going to see positive 1,000. I just have positive 1,000. So it goes up to 1,000 pounds. From point B to point C, we don't see any other torque, so 1,000 pounds it's gonna show up from point B to C, and exactly at point C we are gonna have negative 999, which is almost 1,000, and from point C to D we are gonna have 0 torque. So the torque is gonna show up from point B up to point C. So by looking at this, any point from point B to C would be the critical section based on the torque. So I'm looking at this, I'm looking at that. Section B is the critical section. Section B is going to have the normal stress due to the bending moment and shear stress due to distortion. So sigma would be M at point B times C, which is D over 2, pi D power 4 divided by 64, 32M divided by pi D power 2. So sigma B would be 1972 pi d power 3. So it's gonna be 276 over pi d power 3. We are gonna find d at the end. And due to the torque, shear stress is gonna be T times C divided by J. It's gonna be T times D over 2. J is pi d power 4 over 32, or 16T divided by pi d power 2. The torque is 1000 pi d power 3. So we have shear stress, we have normal stress. Now we should decide which criteria we are going to use. Let's use flow theory for now. I'm going to use modified Moore theory later on. If I want to use CMP, I should know where are we on this plane stress element. We have plane stress element because we have only normal stress and the shear stress. I need to find first sigma A and sigma B. Sigma A and sigma B would be sigma X, which is 276 pi d power 3 divided by 2 plus and minus square root of plus shear stress square. 1592.9 pi d power 2. If I do the math, sigma A is gonna be 21.94 divided by t power 3 kpsi. Sigma B would be negative 1.22 pi d power 3 kpsi. D is unknown, we are solving for D. There is no pi here. So D is always positive, 21 is positive, so sigma A is positive. But sigma B is negative. So sigma A is positive, sigma B is negative. I end up to equation 531b. I'm gonna solve for this one. For the diameter, by considering factor of safety equal to 2.8. Let me finish this example tomorrow.